Hi everyone, welcome to our final project showcase video for ECE 3710. My name is Lucas Pernew. I'm a computer engineering sophomore.
My name is Cole Francis. I'm a computer engineering junior. For our project, we created a digital synthesizer with a keypad input for our keyboard, and then 4 different instrument controls, and also loop pedal functions. And we wanted to do this because Lucas and I are both, we love sound design, we love instruments. We both play bass, he plays guitar. So this sort of drove our interest in this project idea.
To start, we're using the keypad for our input as a keyboard. We're using these 12 keys for different notes in an octave, and the top 4 keys change the octaves we're playing.
As we said earlier, on our project, we implemented different instruments by outputting different waveforms through our amplifier. So we have 4 different buttons here, and each of them controls a different instrument you can play. We have a sine wave with a nice, clean, smooth sound, a square wave, which is a lot more retro sounds, a sawtooth wave, which is also the different retro sounds, and finally, random noise for a drum type instrument. And then these 4 buttons on the right side, these are to control our looping functionality. This allows us to record a section of music and then loop it back, play it back while playing a harmony or a melody on top. For example, if I start recording, I can now play it back and even play harmony on top of it. And this final button here clears the memory, resets the song. Notice right here we have 2 potentiometers. One of them controls the sound level of our basic output, and the other one controls the sound output of our looping. So this allows full dual channel control of both our manual output as well as the recorded output. To implement our looping functionality, we designed our own simplified version of the MIDI protocol, where we save notes based on events of starting a note or stopping. We save a table here with a table with 512 entries to allow good duration of music. We have a ballad bit, time since last event, instrument, pitch, and start and stop. So as an example, if I were to play a note on the keyboard, we'd first set the valid bit to true and save time since last event. We use an internal counter based on a timer incremented at a constant 240 hertz. And so we use that to say the time since last event. Let's say, since this is the first note, that's since the beginning of our recording. And then we save our instrument, our pitch, and whether it was a start or stopping a note. And when a player releases the button, we save one more entry to the table. We set the time since last event, so that would be the duration of the note. For the stopping the notes, we don't have to care about instrument or pitch because that was already set. And then we'd specify it was a stop bit. To implement our different instruments, we saved samples of a specific waveform over a period. In our case, we saved 360 samples of a waveform inside a lookup table. And that way we were able to add in custom waveforms, whatever we wanted. If we wanted to play a triangle wave, we'd record, we'd save 360 samples of a triangle wave and just put it inside this table. If we wanted a completely different sound, we just need to record 360 samples over one period of that sound's waveform.
With those lookup tables for the sine or sawtooth waves, to get different pitches, we changed how fast we step through those tables to output that waveform at a higher or lower frequency. We originally had thought to do this by changing how fast the timer ran, and changing the ARR or PSC value to adjust that for the frequency. We found it actually simpler to keep the digital to analog converter outputting at a constant rate, but instead changing how far we jumped through the table for different pitches. So we saved for each of our 48 different pitches, we saved a value corresponding to the number of degrees to step in one time step, scaled by a factor of 1024, so that we could keep fractional accuracy without dealing with floating point numbers. Then at the end, as we looked up what the next value in the table was to jump to, we scaled back down to get a value of degrees of how far to step through the table, which is why we had 360 entries in the lookup tables. We had a lookup for each of those 48 values for how far to jump for each pitch, and that allowed us to output different frequencies even with our DAC going at a constant rate. Once we have those values that are output from the lookup tables, we send those to our digital to analog converters. And we're using both channels of the DAC. One of them is used for our manual output, the notes we actually play, and the other is used for the notes we've recorded and are playing back. Once those values come from the digital to analog converters from the microcontroller, they're sent through a simple RC high pass filter to remove the DC offset so that we don't blow our speaker with it. That is then run into an op amp serving as a buffer so that the rest of the circuit doesn't load that filter and change the cutoff frequency. It is then run into potentiometers to control the volume, so we can quiet our recording or quiet the notes that we're playing. And those outputs are then run into another op amp serving as a summing amplifier to combine them into one single output. This op amp also scales down the voltage to a level that a guitar amp would expect so that we can use that voltage safely. It is then run into a simple 1/4 inch jack and my guitar amp where we're able to hear the sound. In our original design requirements, we had talked about removing that DC offset using a differencing amplifier to subtract out the DC offset, but by using the simple RC filter and then a buffer, we were able to remove that DC offset without having to figure out ourselves how much of an offset it would be. So we didn't have to be as precise. We could just let the filter do the job.
So all in all, we were able to meet all of our design requirements that we specified in our document. As we mentioned in the video, there were 2 requirements that we decided to adjust slightly once we figured out a better solution. Those were changing our pitches. We stepped through the table at different rates rather than updating the digital to analog converter at different rates. And then we also removed the DC offset through a high pass filter rather than a difference amplifier. Both of these trade-offs led to better solutions with little to no sacrifice and allowed us to meet all of our design requirements while getting a working finished product.